Hi there. Today I'm going to show you how to implement a CNN network from scratch. So let's dig into the data set that I'm using here, which is nothing but the CIFAR 10 data set. Let's talk a minute about what is this data set. This data set is a collection of images like real images. They can be like belonging to any of the 10 classes that we'll just go through. So this data set contains of totally 60,000 color images, which are of resolution 32 by 32, and they come in 10 classes. Those 10 classes include airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So these are the possible 10 classes that we have. And out of the 60,000 images, 50,000 are training images and 10,000 are test images. So the data set is divided into 5 training batches. We cannot train the model on 50,000 images entirely at a time. So we split 50,000 into 5 batches of equal size, which is 10,000 images. So that's the training batch, and that will leave us with 1,000 images. I'm sorry, that will leave us with the 10,000 images for the test batch. So the test batch contains exactly 1,000 randomly selected images from each of the classes I just mentioned. So important point here is the classes are mutually exclusive. That means image can belong only to one class and not cannot be included in two classes. So this is where you can download the list. And the important thing about this data set is that the input that is available to us is pickled data. So we are going to have to unpickle the data first into Python objects so that we can access the images as images. And since we are dealing with image classification here, so we definitely have to unpickle the data that we have. So since this is an the depth of these images are 3, which is nothing but RGB. So the first 1024 entries contain they explain for the red channel values, and the next 1024 pixel values will account for the green channel, and simultaneously the other one will be blue channel. So and let's have a look at the data first. So here we are defining the path. So this is where I have placed I have downloaded the data and then uploaded into this remote server. So this is a remote server. I have started the instance and uploaded the required files. After placing them in the required subfolder and defining a path here. So I'll be using this path here later in the code so that I can extract the data. Like I said, since this data is pickle is nothing but Python objects which are converted into only Python understandable script. So that is why we are going to unpickle to again visualize the images. So we are defining this unpickle function here, and with file open, that's a common thing about how we open files. So in the part of the code, we use RB here. So R is for only reading. We are not going to write over the data, and the B there represents the binary coding, and we are interested in converting to the pickle data into byte form and then reading the byte form to understand what are the Python objects actually they are. So I'm going to use the RB method and the encoding will be bytes. So, and we are assigning this to a dictionary. We'll understand why dictionary and which returns the same dictionary. So here we have like about 7 files, 5 testing data, training data, 1 testing batch, and metadata. So we're all going to assign we just have defined a function here. Using that function, we are going to you know um, add these data into this variables. So that is done in this for loop. So here we are using zip so that this all each respective index value is assigned to exactly only this one, and once assigned it cannot be changed. So that's the purpose of using zip here. So we're listing the type. So this one is just for my clarity while I was coding. So this is just to understand the data type of the variables that I'm dealing here with. So this dictionaries, when do they come into picture? So using this for loop, we now assigned all data of zero index to be batches meta. So let's read what is the content of the batch meta. So here we can see that number of cases in the batch, it's telling us there are 10,000, and the label names. So we have 10 classes, so all those classes will be given here, and number of pixel values. So like I previously said, 1024, and three channels we have RGB. So 1024 into 3, which makes 3072. So this is kind of a dictionary, because this one has this key has this value, and this key has a list of values, and the last key has a numeric value. So that is why we assign dictionaries initially. And now let's look into batch data one. And of course we can test everything, but let's just look at the keys first. So the keys are, first is batch label. And what is the label? Here the data. So data is nothing but the image data. We'll just talk about that. And the file names. So each image is usually having a name, so that is what they are calling as a file name. So if you want, we can have a look like this. What is batch data? So let me run it for you. Let's wait for a minute, just a minute. So here we are. So it is telling us what is the batch label. Since we are reading training batch 1 out of 5, so it is telling the batch label as batch 1 of 5. And what are the labels? Each label includes these 10 classes starting from 0 to 9. So whatever label the image has, it is showing a list of these values. After which we have coming up arrays. So arrays, we are representing the image data. So it's here. So this is for the first row. This is for the second row. Similarly for the nth row. So here these arrays contain 3072 pixel values, accounting for RG and B channels. So likewise the names. The names, as we can see here, each of them have their own way, but we don't really deal with these names. We are only interested in the classification. So we'll be only looking at the data of this image, as well as which class it falls into, and we'll call these as labels. So again, we'll just go back here. So let's have a look at the length of the data. See, the length of the data is 10,000, which means we have 50,000 training images, and we are just reading out one batch here. So 50,000, each contains, there are 5 batches in total. So each batch contains 10,000 images. And like previously said, 1024 pixels, input pixels for each channel, which makes 3. So that's 1024 into 3. This is the length of each row. So I have used the index 0 to find out that. And now, since that we have discussed about what is the data and how it is read, and how it looks after reading, let's start visualizing. So for this purpose, we are using the matplotlib.pyplot. This is a common library for Python visualizations. So we are reading the since that is a dictionary, we'll be calling only whatever row we require, and we'll be assigning that to X. So this is the thing, that is how we are assigning. Since we know the label, the dictionary key value here as B data, so we'll be using that B data of initial batch name. and we'll be assigning them to X. Here we are going to reshape the image, because an image is usually represented with height with depth, height, width, and then the depth. As you can see, 3 is our color channel. That means this must be our depth, so we don't have it in the right place. This is the number of images, and our image size would be 32 by 32 by 3. So we are going to transpose this array, and that we reshape like this. So we want 10,000 where it is. We don't have to worry about that. So this is 3 which we have to worry. We just can't simply exchange 3 with the last 32. But this is because we don't want to mess up the image data. So if image data is messed up, there is no use in what we are going to train. So that is the reason we are going to do this. So 32 by 32. So this like Python goes by the index values ranging from 0 to n minus 1. So since there are 4 here, we are going to use 3 index values. So 3 is going to move to the last place. So 3, the last place has this 1 value, and this 32 moves here. So that is how and this one comes here. Then this will have 0 as 0's place. This 32 is going to have the last value. So here this is going to move here, and this 32 is going to come here. So this goes here, and this 3 is being replaced by this 32. So that is how we take the transpose. And using the max function, we are trying to identify the largest value of the pixel. So it seems to be 225, and we are going to normalize the image data so that we can better handle the data during the processing. So we'll be dividing it with 225, and to see if the maximum value is 1. So if we plot any image, it would appear like this. So this is another image, and this is next in line. So that leads us to one hot coding. Why do we need one hot coding? Because our data here is integer coded, which means the classes 0 to 9, each representing a different class. But how does the system understand what number is for what class? So for that purpose, we are going to convert into one hot coding, where one hot coding, it will create an array of zeros. So if the class is one, it will have a one placed at level 1, and if it is class 2, it will have a one place at index value 2, and all others will be 0. Similarly, if the image belongs to a class 9, it will place a 1 at the ninth value, and all other values will be 0. So that is how they represent a one hot encoding, and it will be the most easier one for the machine to process. Now let's move on to setting up the images and making it ready to feed into our convolution layers. So here we are defining a class CIFAR help. This is going to help us a lot later. So the same thing, we are going to reshape and assign them, and then we are going to see each image has a respective label. So we are going to use this one hot coding encode function here that we have described here, and we are going to convert it we are going to convert that label into its respective encoded label. So that is what is being done here. And now we are defining the batch size here. So in batch size, we are specifying a value of 100. It means that it's like a kind of mini batch thing. I think that would help people understand even more easily who have an idea of the neural networks. And then we are calling the CIFAR dot setup images. So this we are going to use in the end while running. So I'm going to skip this one now. Okay, before digging into CNN network, I'm talking from a perspective of who is already aware of what CNN networks are, and basically convolution, but for the fresh eye people, I'm just going to get through you a review. So basically convolution networks, how they work is by taking an input and convoluting through those images, which means a filter will be taken, which moves over the input image. This is called a receptive field. It calculates uh, weights based assigned to the filter, and it multiplies with the initial matrix and brings us the output. Here we lose information, but the main feature from that receptive field is captured. So we move over the entire what to say image without and extract features. So in convolution layers, that is what happened, we extract the images, and there are a lot of parameters included here. So the receptive field, by how many elements you move the receptive field, that is called as a stride. And since we are convoluting a small matrix over a large matrix, with the dimensions of the matrix are considerably reduced. So if we want to avoid that thing happen, we just consider an outer padding layer. And also, if you notice, while moving a small matrix over a bigger matrix, the elements in the inside are repetitively considered, but the border elements which are on the edge, they are considered only once. So there's a chance to lose information from the outer layer. And for that reason, to avoid that one, we'll be using the padding layer for convolution layers only. So that's a bit of what is a convolution layer. So we have more layers, and that I will definitely take you through. So the first task for me here right now is defining the supporting functions for building the CNN. So the first one will be initializing the weights. So for initializing the weights, I'm defining a function here. The input will be the shape of the filter. So here I'm going to use a normal distribution whose standard deviation will be 0.1, and given the shape of the filter, it will generate a normal random numbers, but they do follow the random distribution, and they store them in a TF variable. So similarly, bias, we after multiplying the matrices, we definitely need a bias value to add to the output equation which predicts the classification. So here we are going to define the initialize function, and this will take, this initial value will be constant because the bias will be updated during the networks. So setting up the convolution layer, so here we are defining another function which takes the inputs, which are nothing but the image data and the filter shape. Once the filter is initialized with weights by calling the function, the weights are also given. It will process the convolution layer to so here, like I previously said, stride is the number of elements by which it moves, and it returns the outputs. So convolution layer always goes hand with ReLU layer. So this is an activation layer. Here nothing is done except processing the data. So we are going to create a ReLU layer. So the convolution layer outputs are fed into this one, and the filter shape is specified. To the ReLU output layer, bias is added. So inputs plus bias is added. After that, we set a pooling layer. So in the since we have to deal with many neurons and we have a lot of pixel values, so we are going to consider max pool. So max pool reduces the spatial size of the matrices without potentially affecting the data in image data. So in the max pool, we are using a stride 2, which means the output size of the matrix will be halved here. And for pooling layer, we generally use a padding method equal to same here. So these pooling layer outputs will be next fed into the fully connected layers. The fully connected layers perform the computation. So we have the inputs, we have the weights initialized, we have the bias calculated. Now the weights are multiplied with the inputs and bias is added. So this is fully layer connected. And now we are going to start building the convolution network. So we need two placeholder values, one for the input data and other for the prediction variable. So we don't know the size of the row, so that's why we specify none here. But we do know, what we know is the image input size, which is 32 by 32 by 3, and the output, it's 10 classes. So we are not going to need reshape here, but in later, before, after the convolution layer and before feeding it to the FC layers, we need reshape there. So this is how we create the first convolution layer. This is the image input data, and the filter shape we have specified here. So here I'm using a filter of 5 by 5, and this one is now we using the functions defined previously, we are going to get the calculations done. So the calculation part is involved in the loops functions defined above. So these outputs are used as the inputs to the ReLU layer 1. So here if you see, these outputs are going to ReLU layer 1. This is a filter shape. Similarly, pooling layer, these outputs, the previous outputs are inputs for the pooling layer. Just similar to these convolution layer, we add another convolution layer here. So now the outputs of these final pooling layer will be flattened and converted into an array and then sent to the let's say the first fully connected layer. In the fully connected layer, we have all the inputs that are multiplied with weights, and then the bias is added. So that one will be passed on to the next connecting layer. So here we have a dropout layer. Because we have a lot of information that has been processed, we are going to hold few of them and then finally come up with classes. So that is why we are having this hold probability, and this one we are going to use as 50% while running. So this is how the fully connected layer and final outputs are obtained. So we definitely forgot about mentioning the loss function. So the loss function, while calculating, we definitely encounter with loss. And since this is a multi-class classification, we are going to use a softmax cross entropy loss. And the optimizer that we are going to use is Adam optimizer. So we are going to train the model using this, and the learning rate is 0.001. Learning rate is usually preferred to be less than 0.1. I'm not really sure of why they are using at this moment, but I'll definitely come up with the reason by a little research. So this is how we are building CNN trainer model. So optimizer dot minimize, and we are minimizing the loss here. So now we initiate all the variables and we decide the steps to be 5,000. The steps can be just an arbitrary number. I'm going with 5,000 here. Now we are running the session, and so what's happening in these 5,000 steps? We want to visualize that. So for every 100 images process, we want to print the step accuracy. So for the first step, when it is running, we run the ses.run and train the model. Here the input will be, X will be nothing but our image data, and Y true will be our images labels, which are one hot encoded, and the whole probability in the dropout layer after the final connected layer will be 0.5. So for every 100 images, we are printing the data. So we use a loop if I mod 100 equal to 0, and we are printing the accuracy at which step. So how do we do this? If the trained model has predicted correctly, I mean, if it is of the same class and the model also identified of the same class, then we decide it is a match. So if matches is equal to this one, then we'll have a count against it. So accuracy is will be will be casting these matches from integers to float and then calculate the accuracy using the mean of the matches. So we'll definitely have many matches. So how do we come up with one value for that? So we'll definitely take mean, and that is how we are doing. Similarly, after training, we uh, uh, go for the test. So when we are going for the test, what we have here is accuracy that is calculated, and the feed dictionary. Here the feed dictionary, here it will be our test images. So like previously mentioned, this ch, we are going to call this one ch test images, as x test images are nothing but the data that we want to analyze from the test images, and labels. So in the test layer, we do not have a probability of 50%. We want the best results, so the probability will be 1 or 100%. So we are going to print the accuracy. So if you observe here, let's look at the results. On step 1, it is 13%, and step 100, it has gone to 38%. So the first step will definitely have the lowest accuracies, because it hasn't learned yet. It just started learning. And upon iterations over steps, we can see that the accuracy is increasing 38 to 49, 55, and so on. It reaches 60s, 65, and 67. Oh my god, the 67 is the highest until now. So let's end up at the final step. We have really reached a final percentage of 68.5%. So this is about building a convolution network from scratch and testing the accuracy. So we can do various updates on this model. So we can add a third convolution layer, which I have done exactly like the previous one, but including an extra layer and passing the respective outputs. Oh my god, I think I have shown the fourth layer as well. So the accuracy levels are only 64%. So I would consider a third layer is even better. So I have shown you with this 4 layers, and now it's for 3 layers. So let's have a look at that. So here is the first layer, second layer, and then the third layer. Okay, this is also fourth layer. I might have a copy where I use 3 layers. Let's look at the output for 3 layers. I want this to be 3 layers. Okay, yeah, this is 3 layers. So this is second layer, and then this is third layer. So we do not have to, I mean, we should not forget updating the respective outputs, or else we are going to end up with mistakes that are silly. So for third layer, if we see, the output is again 64. So whether we use 2 layers or 3 layers or 4 layers, the performance is not very much affected. It is almost in the same range, like 65, 2% plus or minus, because each time we run, this percentage changes from 2% up and down. So that's why. And we can also change these step values. I have even done trial and error methods using that, but I haven't really noticed any significant changes. So I'm going to stick with the updated model as reduce step size with 3 layers, and that also has shown only about 65% of accuracy. So I would say maybe some technical issues, maybe my coding was not very well good enough. So potential changes that I would suggest for this model after looking at the accuracy values would be L2 regularization, and maybe image resizing. I am not really sure about that image resizing because I haven't done it yet, but that's worth a try. And that's all about convolution network from the scratch. So I'll just walk you through the report that I have been working on. So just give me a minute. I just want to zoom this. So the report on the result. This is the base model. Here initially it was 13%. As the steps increase, it has ranged from 38 to 61 and finally ended up at 68.52%. So what is the 68.5% mean? So we can be out of 100 times, 68 times the model lands on correct classification. So that is 68% means here. So 68% of times the classification results are true. There's a comparison between the models. Okay, here we have previously worked on MNIST with the same convolution layer, and the test accuracies are compared here. So for the MNIST data set, it is 98, while it is for 68 for CIFAR data set. That is because maybe the data processing has been simpler. The MNIST is a grayscale, so the depth will be 1. Here it is a 3 tricolor, so it is 3, and which requires much more processing. And these would be the technical uh, improvement suggestions: learning rate, increasing the batch size, increasing the model capacity, and like I said, image resolutions and random rotations and shifts, fine tuning of the model. This includes like dropping out some overly sampled data classes, and class weights using by training highly imbalanced databases. Class weights will give equal amount of importance to all the classes during this training. So fine tuning the model and training data. So I think that would be it. This is the updated model which I have already discussed. So this just report on what I've been explaining right now. Thank you.